Okay, it was a great pleasure to start the workshop with Mason Porter, who's going to talk about social dynamics on networks. Thank you very much.
Thank you for the chance. I'm not going to wait to do this. Oh, you can't hear it. Okay. Button on the top. I'm sorry. What? Okay. Is that better? All right. All right. Take two or take, I don't know, we were supposed to do this 2 years ago, take 10. All right. So it's great to do this in person. Seeing people in person, it's just okay. I've actually posted these slides on SlideShare and tweeted that. So if you want copies of the slides, you can already look at it and follow along. And I can attempt to. I'm completely jet lagged, so this is going to be a horrible talk. I'm sorry. Okay, so first let me start with some review articles. These are not the only review articles that exist. But if you want to learn about social dynamics and it's not something you already do, these are good places to look. There's a couple different review articles by Hossein Nourazar and various co-authors. The one I'm highlighting is this particular one, and it has a bunch of classical models and a bunch of more recent models. And then there are people from the quantum realm here. I'm using the English meaning of the word classical, not the physics meaning of the word classical. There's an older article by Claudio Castellano and Santo Fortunato and Vittorio Loreto. There's been a lot of stuff since then, but it still has some good places to start. And then on a more specific sort of family of models, there is an edited book, a collection from Suni Lehman and YY On. Most of the chapters in that book, I think, are available on archive. So you can get most of them without paying Springer $200. Okay, so I'm going to have the first set of slides within this deck are actually are new, and it's mostly to sort of set the stage. And I tried to take seriously that this is an overview talk and to bring up some issues that people think about. And then I will give some examples from some of my own papers, just as concrete illustrations. They are very specific examples. They are not intended to say, oh, this is a particularly important work or whatnot. It's just to make these ideas concrete. And I'm using my own papers for that because I know them better than I know other people's papers, right? Very simple reason. Okay, so there's a lot of different models and that are meant to do different things. And this will, including in terms of what types of mathematical approximations people use or what types of questions people ask and try to answer with them. And then I'm sure that many of you who work on some related topics will think of models or questions that are important that I don't think of, and those will be good for discussion sections. So one thing that people think about is consensus versus polarization versus fragmentation. And the term polarization is not always used in the same way. So here I'm thinking of maybe two groups at steady state, but some people will use polarization to mean 2+. And then when I distinguish them from fragmentation, I'm thinking of 3+ groups at steady state. Okay, so you could ask, if I have some model of opinions changing, under what conditions do I get a consensus and how fast do I get it? And under what conditions do I get a polarization? Under what conditions do I get fragmentation? So whether you get it, if there's some kind of phase transition or bifurcation and so on. A point also to mention here is if I get 3+ states, it better not be a 2-state model, right? Okay, another type of question that people ask about or study, cascades in virality. How far do things spread? How fast do they spread? So maybe a meme, something you're sharing on Twitter or whatnot. When do things go viral and when do they not? And in practice, how do you actually measure it? Maybe you measure the structure of some kind of spreading tree. Maybe you do a percolation-like calculation and try to search for a giant component. Or in practice, though, of course, we don't have we don't have the number of nodes going to infinity. Maybe you do something else. Another thing people think about, and this is one reason I'm making this point, is that social dynamics is very hard to actually trust your model as being good certainly as being correct in any sense of the word. So you could say, oh, maybe I shouldn't work on this at all because how can we ever justify one of these models? Except that if you're going to study disease dynamics and actually try to get policy, if you ignore the fact that humans are behaving in a certain way, you are missing a very vital component that you just cannot ignore. So I would say that the answer of I cannot study social dynamics because I can never possibly trust it is a cop out, in my view. So incorporating these models into the models of the spread of diseases is something that I consider to be very important, and there are efforts to do that. And the question is, well, how do you actually do it? How do you do it well? And then a more general question that arises in all these things, and it's not exclusive to social dynamics by any stretch of the imagination, but it does show up in this, is that you want to investigate the effects of network structure on dynamical processes. If you have some sort of non-trivial network connectivity, how does that affect things? Does it make consensus more likely? Does it make it less likely? Does it make a disease spread more? Does it make synchronization more easier to occur? And there's also a vice versa, where dynamical processes can also affect structure. So in adaptive co-evolving networks, if somebody is sick, they better stay home, the network structure changes, right? So there's coupling both from the structure to the dynamics, and you want to know how the structure affects the dynamics, and from the dynamics to the structure. In general, I mean, given models will not have all these. One useful thing that people often do is to make good choices of synthetic networks to be helpful for insights. These networks may not be very realistic. It may be a sort of random graph model, or it may be it may be it may be a deterministic model that's not realistic. But you know more about that structure, and that can therefore help you learn something. Okay, some challenges. Can we ever do this in a way that's even remotely correct? Yeah, I don't know. That's a very blunt way of phrasing it, right? But maybe they can still be insightful or helpful. You know, this is not measuring forces in a physics laboratory, right? We're never going to reach that stage. So the question is, what can we do? Um, and how do you connect these models and behavior of the models? So in this case, I mean behavior as in dynamics, not like human behavior, with real life and real data. These are really fun to study as dynamical systems and network problems, and you can do some very rich things, but it's a much harder situation to say, well, what do we learn, if anything, about real life? So for instance, there are some models that have continuous valued opinions. Famous example, these are known as bounded confidence models. I'll give some more information about those a bit later. And they might say that I'm going to have opinions on a scale from -1 to 1, where -1 is, say, the most liberal perhaps, and +1 is the most conservative. But if I look at somebody's behavior in real life and what information they're spreading or what text they're writing, can I reliably actually measure where they are on that axis? How might I do that? Maybe based on online fingerprints, um, or based on answers to a social survey or something. Another thing that one could do, instead of measuring, say, opinions directly, and I think the second one, there's a bit more hope, is to compare. There's some efforts to compare outputs of things. So, for example, tweets will have spreading. They're called spreading trees sometimes. They're really directed acyclic graphs, but you can have something that spreads both vertically. I tweet something, somebody retweets me, somebody retweets them, but you can also have things that have a width in addition to a height. Maybe 12 people retweet me, there's a width of 12. And so maybe certain types of memes or certain types of other things that are spreading might have different characteristics depending on their quality or something else. And so maybe you can compare the properties of these trees that are outputs of the model with actual spreading trees. And that's a little bit more reliable in terms of existence of real data, because you can actually look to retreating branches and so on. And so maybe that type of comparison is closer on the horizon than comparing literal opinions of people. One paper that asked a question about a particular family of models is the voter model a model for voters? Okay, so the here should be in quotes. Is actually, importantly, there's more than one variant of a voter model. But Juan Fernandez Gracia and others asked about this, and they don't have a conclusive answer in their paper, but this is an interesting paper to take a look at with respect to that type of question. There are also, in terms of some versions of evaluating these models, and it's not something I'll talk about in detail today, but it's something to keep in mind, especially when it comes to things like online fingerprints. There are ethical considerations in what you actually even should measure to attempt to evaluate models like this, right? So we're talking about humans. There are issues with measuring humans. One has to think about that. And then a more general thing related to a bunch of other things on this slide, there's going to be complexity of the models versus mathematical analysis of them. A lot of the opinion models that are most readily studied from a mathematical perspective are the simplest of these models, and you can say something about them. But if you start adding more complexity, maybe it'll be harder to analyze, but it'll still have a little more elements of reality. So there's a balance, and that type of balance is not unique to social dynamics models. It occurs in any of these models that we're ever studying. But this is a medium where those things come into play. Okay, so various types, a non-comprehensive list. So one thing that people do are compartmental models. This actually comes from disease dynamics, but has been used. So that's one thing. And this has the advantage of there's a rich literature and understanding of how to deal with these models. There are what's known sometimes as threshold models. These have a very percolation-like flavor. So it's like what's known as percolation. There are voter models. There are majority vote models, which is not the same thing. There are majority rule models, which is also not the same thing. There are degree French models, which is a consensus type model. There's bounded confidence models. You can do things through games on networks and so on and so forth. Some of these can be expressed in terms of each other. Okay, so there are, for instance, there are results that certain types of threshold models can actually be written down as a type of game on a network. So there's more than one description that's possible. Discrete states versus opinion states. That should say continuous valued states. Hell, I was tired when I did that. So discrete states versus continuous valued states. Those are two different flavors. They'll have different things going on. Deterministic update rules versus stochastic update rules. I said compartmental models, like the SIR, susceptible, infected, recovered model, but there are stochastic process versions of it, and there are deterministic versions of it, right? So even the same thing, there are different flavors of it that you study in different ways and for different purposes. So you can also talk about dynamical systems versus stochastic processes. Talk about synchronous updating. I said of node states, could be edge states, of node states versus asynchronous updating. So there are often, for a given type of model, there's often different flavors of it. And I mentioned that note below already. Okay, so people study different types of phenomena using these different types of models. That's a very generic thing, but it's still useful to put it out there. So in threshold models, some of the things that people study, they are built to have cascades. They are very percolation-like. They are built to do this. You can therefore consider virality, and there's also something that people consider related to it known as influence maximization. Think of that, one way of doing that as, say, if I were going to spread a rumor about, okay, I wore my shirt today, my secret Jewish space laser shirt, Mazel Tov. If I were going to spread rumors about that, I have a fake news shirt too. I will try to remember to wear that another day. I'm not joking, I do actually have a fake news shirt. It has news in it, GNUS. Okay, if I were going to try to spread something about Jewish space lasers, who would I try to influence to spread it the farthest? So notion of influence maximization, that's one version of it. In voter models, you might examine consensus versus polarization. Standard voter model has two different states. So do you get to a steady state that everyone has the same state, for instance? Or in a bounded confidence model, and this has continuous valued opinions, I might examine consensus versus polarization versus fragmentation. And when you have these different qualitatively different steady states, you can of course do things with bifurcations and phase transitions and ask how that's different on different types of networks. And soon you're going down the rabbit hole of questions that many of us like to ask. Different types of models also have different mathematical approaches to them. We often use the word mean field theory, or mean field theories, really, in a lot of these models. They have different flavors. They don't look the same, and some of them we know more about than others. The ones from bounded confidence models look very kinetic-like, such as in what occurs in models of collective behavior. If you're going to have a mean field theory, mean field model for those. In other notions, you have degree-based mean field theories, where there's a parameterization by the degrees, the number of neighbors of a node. And so maybe you have the same formula, but it just depends on the degree. So there's a bunch of those. There are what are called pair approximations. I will mention a little bit more about that later. And you might have these in threshold models and in the compartmental type models and so on. In these threshold models, branching process calculations and percolation-based methods are often very useful. The models are built for those things to be good approaches. Something else that shows up, approximate master equations. These are all Googleable if you want to actually look up the specifics. And then another thing that can arise, and especially if you're thinking about the same type of model, but written down in a different mathematical way, if I write down a deterministic model, I might use dynamical systems approaches, but I might, if I write down a stochastic model, use more probabilistic approaches. So the types of arguments that I'm using, although there are certain things that are spiritually similar, I'm not sure what the mathematical notation is for that. They are still inherently different in other respects. And you can take certain models that are, say, probabilistic, and you can relax them and turn them into a dynamical systems model that has the probabilistic one in the limit. So you have like a smooth function at some point, which can get to a piecewise smooth function in the limit. And so then the limiting model is traditionally analyzed in a different mathematical way from your other model. And if you're going to actually, think about that limit, you have to deal with that. Okay, another thing we like to do, and again, this is not restricted to the sorts of social dynamics models, but it's true in any sort of dynamical system or stochastic process that we like to put on networks. Let's generalize the network structure instead of just having a graph, having an adjacency matrix. Make it more complicated. How does that change what's going on, right? I mean, there's paper after paper on this, myself included, of course. You might have a multi-layer network. How does that change things? Or a network that's time dependent, known as a temporal network, how does that change things? Adaptive, aka co-evolving network, how does that change it? Or maybe you have more than just dyadic interactions, you have polyadic interactions like in a hypergraph. How does that change it? So how do such more general structures affect dynamics? And if I pick two different styles of opinion models, are there situations that are going to have similar effects on both? Because if I can't trust my opinion model completely, and I don't think we ever truly can, hopefully there are certain types of generalizations that will have similar qualitative effects on different models, because there's going to be stuff I can't ever fully trust. So one thing that we want to know is what new phenomena that occur that cannot arise in simpler situations, right? Just making it more complicated for the sake of more complicated, which often many papers feel like they're doing, is not enough, right? You want something that you cannot already get in a simpler way. There are multiple choices, sometimes seemingly very, very specific and picky for how to do generalizations, but actually they can matter very much for how things behave. So I'm very detail oriented. I think the details do matter, and you have to make a choice, but you shouldn't assume that, oh, that's the natural choice automatically. And so so I make some generalization. Maybe I do polyadic interactions instead of only dyadic interactions. So I allow as many nodes to interact at once as I want. Which ways of doing that makes consensus more likely? And which ones make it less likely? And the answer might be different for different types of models. And then you perhaps can worry a little bit, because if I cannot justify which model is right, but the same network generalization has a different effect on different models, I worry. So you want to try to find situations that are consistent if you can. When is convergence to a steady state sped up, and when is it slowed down? Similar type of question. When is virality more likely? When is it less likely? So this is this last point that I was making earlier, but it's worth repeating because I think it's important. And if you do find things like that, I think it's good to point things out like that in your papers. If you do the same type of generalization on different types of models, say you do it on a voter model versus a bounded confidence model, when does it have a similar effect? So let's suppose I want to add polyadic interactions, and I try to add it in the same way to the extent possible in a voter model and a bounded confidence model. Under what conditions does it promote consensus? And are those conditions the same for the different types of models? Right? Those are things I think it's important to get a handle on, especially because we can't justify the actual mathematical form of the models in the same way that we would, say, in a physics situation. There's also a bunch of application related questions. I'm going to eventually write down equations, I promise you. Some application related questions. Okay, so spread and mitigation of misinformation, disinformation, slightly different from each other, and fake news, formation of echo chambers, the spread of extremist opinions, which is a purely hypothetical question, measuring and forecasting of viral posts, distinguishing internal effects from external ones. So this is a bit of a confounding factor, right? Because if something gets popular enough, then eventually maybe the mainstream media picks it up. And so you can only measure if it's going viral by intrinsic mechanisms up until that point, right? So the experiment somehow, the natural experiment kind of ends at that point. There's also a notion of inverse problems, maybe you can determine patient zero. This is related to influence maximization. Determine like patient zero in the spread of content. A more specific thing that I will mention a little bit depending on time. Majority illusion versus minority illusion. Those are things that one can think of. So it's essentially you're surveying your local neighborhood and you're asking, say, who people are voting for. But if you survey your local neighborhood, it's different from surveying the entire network. And you actually expect this difference to often occur because social networks form with homophily. People who are similar tend to become friends. So it's not just that you can construct networks where this happens, which is not a surprise, but you should expect it to occur because of which networks arise naturally. Okay, other things, I couldn't find a better name for them, sorry. This relates to connecting to things like machine learning and natural language processing, which I think in terms of doing opinion models, there's going to be more of this. And so this is using ideas, say like text analysis and sentiment analysis to infer opinions from textual data. So this relates to the question of, can I measure where somebody's opinion is from -1 to 1? And so some sorts of text analysis and sentiment analysis are ways to try to approach that type of problem. And this can also inspire some inputs, like input probability distributions, say for ideological values of tweets from media, for instance. I'm mentioning examples that I've thought of, and that I have stuff in the pipeline. But these then become things that can interface with the more forward dynamical systems type approaches. And then you can expect there's going to be other connections with tools from machine learning, statistics, and natural language processing, and so on. Okay, so I'm going to start to get a little bit more specific, and I'm going to give a couple examples of these models just so you see concretely what some of them look like. Apologies to people who've seen me give some opinion dynamics talks before, because some of the slides will now start becoming familiar to some of you. So backing up a little bit, just since we're thinking about social networks and things that are occurring on top of social networks, typically, though it doesn't have to be true, let's think of the nodes as representing individuals, and then the edges can represent one or more of various types of social connections. It could be offline interactions, still happen, yay. Phone calls, Facebook friendships. I put it in quotes because I'm thinking of the structure rather than like literal friendships. Twitter followership, and so on. There are notions of actual ties, but there's also notions of communication. And there are some models, including of different types of temporal networks, where you actually want to distinguish things like interactions and social ties. So there are models that distinguish those. Different things will propagate on different types of networks. Information spreading versus disease spreading. We are all way too familiar with this now. And then networks have a complicated mixture of regular and random structures. I put random in quotes because we're thinking of just modeling it as random because we don't know it. And good random graph models are going to provide good baselines for comparison with empirical networks. And this also motivates the study of the random graph models for their own sake, what their properties are, which is in itself a very cool thing to do, a very interesting thing. Okay, so if you want to learn more about dynamical processes on networks, James Gleason and I, some number of years ago, wrote a very short, that's the best thing about this, it is short, tutorial. I think it is readable and it's short. So if it's not readable, then you're at least done with it quickly. Again, incorporates which nodes interact with each other via their edges. This one does not talk about things like polyadic interactions. So it could be also hyperedges. Get a dynamical process on a network, and then this fundamental question that I brought up earlier, true not just for opinion models and social models, but true in general. How does network structure affect dynamics and vice versa? You should be able to download this for free from my website for sure, and there's an archive version anyway. And you can email me and find it if you want. A general note, and I'm not going to go through this slide in detail, and even though I have an hour, I would actually rather have us have a full-length coffee break because I think that's better for all of us, and I also need coffee. I want to make a comment about timescales and models and dynamical processes on networks, because normally these things they're always at least implicit, and I think it's relatively rare for people to state explicitly in their papers what they're doing. And you have to worry about the relative timescales of evolution of states versus evolution of network structure. One of the short chapters in this book has a longer version of this discussion. States could change much faster than the structure. So you might think of a network that is not merely time independent, but static. I actually use those words differently. But you have a dynamical system on a time independent network that is a model-based static network. This is sometimes called quenched. But you could also have it go much faster. Maybe you only trust the statistical properties of the states. The alternative limit is that structure changes much faster than the states. So maybe you think of the states as frozen or not mattering, and you look at temporal networks, but they could change too fast. So maybe you only trust statistical properties of network structure. So then you do a random graph model representing that uncertainty. And then the most generic case, but also then the hardest, because you've thrown less stuff away, is adaptive networks or co-evolving networks. To go back to this first one, since most of today I'm living on that, I think except for one example. So I start a paper and says, okay, I'm going to have a stochastic process or other dynamical process on top of a network that doesn't change in time. So I've already made an assumption. That's my setting, but there's an assumption that goes with me to be allowed to use that setting. So we should be cognizant of that when we're trying to connect it to real phenomena. Okay, so back to spreading and opinion models. There are many types. I gave a laundry list of some types. Compartmental models, hijacked from disease dynamics. Those have the advantage of there's been a lot of stuff studied on them. And so let's use that kind of technical knowledge. Threshold model, this is a type of model that has discrete states, most traditionally 2 of them, but there are some models, some versions that have more than 2. And it can be used to model social reinforcement of a contagious spreading process in a sort of minimalist way. 3 people make a tiger. Voter models, these are also discrete valued, most traditionally with 2 opinions. I would argue it's not really a model for voters, but that's you can look at the paper by those others and see what they said. The initial conditions that occur in voter models and threshold models are different. Threshold models, you usually only have a few nodes starting in an infected state, say it's state 1, and everyone else starting in state 0, and then you have a transition somehow, whatever some rule is, I haven't told you any yet, to go from 0 to 1. Voter models have a different type of initial condition. They start with everybody having some opinion, and then they have a different type of update rule for how things change. So even though it is traditionally a 2-state system, a very different type of initial condition used for different types of questions. Bounded confidence models are a well-known model that has continuous valued opinions. So I will give a little bit more information about each of these. Okay, so first, coupling the spread of opinions and behavior with the spread of a disease, there is a nice, they actually have a review and agenda for integrated disease models, including social and behavioral factors. So a disease model where you ignore what people do is going to be hard to use for actual policy, right? So this article, which has a lot of authors, is something to look at in terms of what questions are people asking. And in disease, the most traditional way of modeling it, it's not the only one, is with a compartmental model. Nodes have different states. These are called compartments. And there are rules for how you transition between them. So one kind is a stochastic SIR model, susceptible, infected, or recovered. Recovered, if you're fatalistic, can also be removed. Nodes in S will change to I with some probability if they have a contact with a node in I. And in this model, nodes in I will recover and change to R with some probability. And you can make these things more complicated while still having S, I, and R. The SIR type models is one model that has been used for opinion dynamics before. Okay, there's a rich history of work on various types of mean field theories. And there is a very nice textbook from István Kiss and others, which is a good place to start for these types of things. Okay, so there are various people who have coupled these, usually in very theoretical settings. This includes us. We are not the first, but again, I know my own work better than others, and I can also advertise the work of my recently former, she was hooded on Thursday, Dr. Kayan Peng is the first author of this paper, so you can look at this work. And this is it's motivated by some things with COVID, but it's really abstracted away quite a bit. We do this on a multi-layer network. I find a multi-layer network framework to be a very convenient way to think about, say, diseases and opinions coupled together. And so in this context, I have one layer that is, say, a physical layer where people are coming into contact so the disease can spread on that layer. And I have one layer, which is, say, an information layer. So any type of communication, again, vastly abstracted it, where we have 2 different opinions that are spreading. There is a pro-physical distancing opinion, and there is an anti-physical distancing opinion. or we're thinking of them as that, but you can just think of them as two competing opinions if you want to make it completely abstract. We assume that people who are anti-physical distancing are more likely to become infected. And we do this in an extremely simplistic, biologically unrealistic way, with the un in front of the correct word. We say that if someone is pro-physical distancing, their transition probability is going to be lower. And if they're anti-physical distancing, their transition probability is going to be higher. Now, that is not biologically realistic, because what would really happen is that the network structure would change, and then you're less likely to have context in the first place. But it is easier to just change the parameter, right? So we've grossly simplified something just to illustrate a point and look at competing opinions on one layer and diseases on the other. But if you wanted to make this realistic, you would, do things in a more elaborate way than we did. And we also used compartmental models for both the opinions and the diseases. So for the diseases, it's very well justified, even though there are some other ways to do things as well. For the opinions, it's less well justified. But if we're going to do a mean field theory, which is something that we spend a lot of time in this paper doing, having the right-hand sides of the two layers, having the same type of mathematical form is extremely convenient, right? So some of the simplifying choices we made are because we know how to work with them, not because they are correct. You can still hopefully learn something by doing it, but it also means there's a lot more to do. And so when I'm talking about balancing of things, you make a simplification because maybe you can do something with it, but you're losing some of the biology. And when is it okay to do that and when is it not? And it's not, I don't find it very clear always when is it okay, when it's not. So this paper is very much a conceptual paper, not one that you're immediately going to do policy, but I think it's interesting in terms of looking at the problem. I am obviously not going to go through this slide in detail. This is the compartmental diagram of the different states that can occur. And even in this very simplistic with respect to real life problem, you can see that there are quite a few different states already just from doing what I described. And some of the equations for the pairs, this is only a subset of the equations. There's really like 15 or something. I don't remember the exact number. Just to show you what they look like. So now this equation is not closed yet the way that I've shown this. And even if I were showing all the equations. So U is saying that you are undecided on the opinion layer. K1 is saying you have K1 neighbors on that layer. I is saying that you're infected on the physical layer and that you have K2 neighbors on that layer. And so what's going to happen is that it may be, how do these types of pairs occur? Well, there may be somebody who's undecided on the first layer and susceptible on the second layer, and who interacts with anybody who's infected no matter what their opinion is. Okay, so you have some triple and you have some transition probability. But you also have some recovery, so these I's can go away, so you're losing some of those. So you do a master equation type of consideration where you have every way of adding more states of this type on the right-hand side and every way of subtracting more states of this type. And because we're using compartmental models on both layers, that means the form of the equations will look the same on both layers. That is very convenient. Okay, this equation is not closed even if I showed all the equations. Why? Because I don't know how triples evolved. So I have two choices. I can approximate how triples evolved via pairs and singles. I haven't actually shown you how singles evolve, but we know how they evolve. It's in the paper. Or I can have on the left-hand side equations for how triples evolved, but then those can come from quartet terms, and so I have to approximate those, right? So a pair approximation is going to be referring to a moment closure at a certain point. So I'm not going into detail, but I hope I've given enough description to indicate what I have in mind and the sort of form of what these look like. I'm going to switch. Whirlwind. That's what papers are for. Okay, another type of model, threshold models. One example is the Watts threshold model, though dates back to Granovetter if you don't have a network, and also Kempe and Kleinberg and Tardush did something in parallel in the almost in parallel in the computer science literature, and Tom Valente actually predated Watts in the social networks literature. So this is a threshold model, and it's very reminiscent of bootstrap percolation. And if you're a probabilist, it's also reminiscent of kinetically constrained models. So each node has some threshold, traditionally frozen, drawn from some distribution. They can be one of two states, either a seed number or a seed fraction of nodes. Start in state 1, think of them as infected and so on. Everyone else starts in state 0. Seed fraction versus seed number. Are you going to put a size scale into the system or not? And then updating can be synchronous or can be asynchronous. Synchronous, I have a map. I update all nodes at once. Asynchronous, I'm thinking of it as a discretization of continuous time. I update, say, one node in a time step DT, which I consider to be very small. It can be more than one node, but traditionally it's one for these models using, say, Gillespie algorithm. And then the update rule is that I compare, in the case of the watch threshold model, the fraction of infected neighbors to this Frozen threshold. And if I'm updating this node, then I'm going to become infected if this peer pressure on the left is more than my latency on the right. And one of the ways of generalizing this type of model is to generalize the expression on the left, what is the peer pressure like, or to generalize the latency on the right. There's some other ways of generalizing as well, but different versions of these models tend to mess around either with the left or right-hand sides of this particular expression. This type of model also has a very extreme situation, which is a monotonicity, and I go from 0 to 1, and I stay there forever. That's not realistic for most cases, so you can think about a couple of applications where it might be okay. There are a couple variants that don't have monotonicity. If you're interested potentially in these types of models and using the types of percolation methods and branching process methods to study them, there is a very nice paper by James Gleason in Physical Review X, and it has a table of quite a few binary state models that some of these types of mathematics can work on. So one of the things that you can do is to look at steady state levels of adoption depending on your initial condition. So for instance, if all nodes have the same threshold of 0.3, so I need at least 30% of my neighbors to be active, to become active itself. This slide I stole from my former postdoc, Sergey Melnik. If I start in the middle, everyone becomes infected or active. If I start over here, I get 5. Start over here, I get 2. And these sort of tree-based mean field theories, these branching processings, what you get, they are time dependent for a lot of these papers, but they are ensemble averages. They are expectations over different initial conditions. So these things are good. These methods are good at resolving things over time, but most of the work in this does not resolve things over initial conditions if you're interested in different bases of attraction. Okay, so where's Jonas? Jonas is here. Jonas is there. So I won't spend much time on this, but Jonas is the first author on this paper, which is one particular generalization. So since he's at this conference, you can therefore ask him. But I wanted to show an example of how to generalize it just to make concrete. So we have the same rule for when I'm going to change. I change from either from 0 to A or from 0 to B. So I have two products and they compete. And a conformance node will do a watch threshold model type of thing as I described. And the hipster node will change at the same time, but instead we'll look at the bestseller list after some time delay and we'll change to whichever product is not the bestseller. The hipster was on the network before it was cool, by the way. This is from from tau time units ago. So we're using synchronous updates on this. That was convenient for this particular generalization. So we chose synchronous updates not because it is correct, but because for this generalization, it was a convenient thing to do. Okay. How can a minority opinion dominate? I will skip in the interest of time, but you can take a look. All right. The voter model, the in quotes is actually important for that. If you want an introduction to voter models, and reality inspired is actually a very nice term for these rather than saying realistic. Sid Redner has a paper from a few years ago. I had actually not even heard of this journal until he published this paper in it. And it has different ways that voter models have been generalized. Okay, so traditional voter model, again, you've got two states. Individuals will update their opinion based on the opinion of a neighbor, but how you choose which nodes are updating and which neighbor you consider is different in different models, and that will affect things such as the convergence rate to consensus. So from certain perspectives, they're actually rather different, even though they have a similar flavor. So you can either choose a random edge, traditionally uniformly at random, or you can choose a random node, right? So you're choosing 1 out of n squared roughly, if you have n nodes, or you're choosing 1 out of n. If you choose a random node, you could then choose a random neighbor. And then one choice, again, another choice is do asynchronous versus synchronous updating. Again. So there's an adaptive voter model that my former student Jakub Kare and I worked on. This was asynchronous edge-based updates. So we're going to choose a random edge. And then from that, we're going to have one of those nodes be a sort of pivot node. And that's the node that's either going to rewire in this case because it's a adaptive model. So this will also give me a chance to introduce adaptive models to you. And we use asynchronous updates. So what we have here is, let me actually, so there's the notion of a discordant edge. In the context of this type of model, that just means that it is attached to two nodes that have different opinions. For other models, like a continuous state model, you would have to think about what it means to define an edge to be discordant in the first place. In this case, you have a definition that comes naturally. Okay, so let's suppose that this node A is the one that we have considered. This is our pivot node. So we've picked this particular edge and we're going to pick A from this edge. So we are kind of, with some probability, A is going to become B. And with some other probability, it is going to break this edge and potentially rewire. The probability is sigma to the Q. This is done differently in our paper than in other papers. This actually relates it to what's called a Q voter model. It's not quite that one either. But as a sigma to the Q probability of choosing to rewire, and as a complementary probability of choosing to change its opinion. So this Q is a nonlinearity parameter, and the probabilities are different depending on the value of Q. And what we do is we look at different qualitative behavior in the paper as a function of this Q, mostly numerically. So if Q is large, then I'm more likely to adopt an opinion, and if Q is small, then I'm more likely to rewire. Okay, so there's a couple different types of rewiring steps that one can do. One possibility is, so let's say I'm rewiring. So rewired at random would mean I choose uniformly at random from all nodes that are available, including the one that I just dumped. That's what this part means. I've dumped this, I've chosen the same one anyway because it's still available. Or I could choose this, or I could choose that. Rewired to same, I'm choosing among only ones with my same state A. And rewired to none, which no longer preserves the total degree, so that can be difficult for certain mean field theories. We were thinking of this in the context of the 2016 elections and people unfriending each other on social media as a result of arguing with each other, or perhaps just finding out things about their friends that they didn't want to find out or something. And so in this case, rewired to none is just unfriending. So this is a schematic of one step. So you might adopt or you might rewire. And again, useful, or I didn't show an example of this before, but I mentioned it. Putting things on good random graph models is convenient. So in this case, we start with a GNP Erdős-Rényi model. So n nodes, independent homogeneous probability P that they are adjacent to each other. And one thing we do is plot. So people plot the number of discordant edges as a function of time, for instance. Do you get to consensus, or do you get to zero discordant edges? And in an adaptive model, because components can disconnect, those are no longer equivalent as they would be if they cannot disconnect. So as a function of Q, and just as a reminder, larger Q means more adopting. Sigma is between 0 and 1 because of the probability. Smaller Q means more rewiring. Okay, so if I have more rewiring, the terminal density of my minority state ends up becoming about 50-50. If I have more adopting, my terminal density minority state becomes not quite 0. This is strictly above 0 because some components have disconnected. Okay, if they didn't, so it's not actually consensus. It's just that there is a strong majority. You can also just say pick a state regardless of whether it's the minority or majority. The initial condition for this one, by the way, is half the nodes in state A and half in state B chosen uniformly at random. You could look at the terminal density of state A, and if you take each x is a mean over some number of numerical simulations, like 20 of them or something, and it's basically saying, well, sometimes A is winning and sometimes B is winning. Blue is an individual, is a steady state outcome of an individual computation. And so you can see, well, sometimes A is winning and sometimes B is winning. You can get more complicated transition behaviors if you do more complicated types of models or more complicated types of graph models. So then again, this is part of the game of saying, well, I'm going to use a more complicated model and see what happens. I believe in practice, I started at 9:13 or something. Okay. I still want to actually give time for discussion and questions. So majority illusion echo chamber is something that I first saw the term majority illusion from Christina Lerman. And we think about it in terms of, we think about majority minority illusion. Okay, another type of model. whirlwind tour. I hope at least these things that I'm mentioning give some idea of what what types of questions people are asking. Again, using my papers just as concrete examples, not because they're more important than others, because they're not. Okay, bounded confidence, continuous opinion states. So for example, it could be -1 to 1. When two agents interact, if their opinions are sufficiently close, that's going to be one parameter in one of the standard versions of these models, they will compromise by some amount, and otherwise in the most standard version, they will not change. There are versions in which they go farther apart. I'm mentioning this now because everyone asked that. Let me give the talk. The two best known variants, one has synchronous updating, one has asynchronous. In this case, asynchronous updating would be updating of, say, 2 nodes if you have dyadic interactions, or updating of 1 hyperedge nodes if you have polyadic interactions, rather than only 1 node as in these other types of models. So Defont-Weisbusch is the traditional asynchronous updating of node states, and the Hegselmann-Krause is the traditional synchronous updating. The most traditional studies are without network structures, but then the question again is, okay, we'll add network structure and what happens? So it's the same type of question I was mentioning earlier. Early motivation for some of these models actually was to examine how extremist ideas, even when seeded in a small portion of the population, could take root. But usually what's been studied, and I think it's just because it's sort of easiest problem within the study and already has very rich phenomena that occurs, is to study what happens with consensus. Is the microphone still okay? I think I knocked it a bit. I'm still okay. Thumbs up, so that's good. I am a mathematician. A subset of people confirm that it's okay. So hopefully that is the representative subset. Let's put this on a network. I will have a larger but fuzzier version of this thing on in the next slide. So one thing I also want to mention, even though I'm concentrating more on the direct science in this, but I'd like to brag about my students because it's one of my favorite things. But my former undergrad, Flora Munn, who either just has or will soon finish, is my student at Oxford. She's the one who actually taught me about bounded confidence models in the first place. He was a senior in Oxford and wanted to find, or a 4th-year student, a Part C student, vocabulary, and wanted to find something to work on. She actually found these, and I hadn't known about these. And since then, I've thought about these a lot. I have a grant on them. I've written a bunch of papers, and I have this whole thread of research. It was because one of my undergraduates found it. So those are it's really awesome to work with. Okay, anyway, so we have a paper. Robert Van Gorder is the other author on this paper. Network structure can have a major effect on dynamics, including how many opinion groups form and how long they take to form. And here you do have to worry about different numbers of groups. Oh, another thing I should mention. I should have mentioned this on this slide. When do you study the DW model or generalization thereof? When do you study HK? So I argue that the asynchronous updating tends to be more realistic usually, but the computations are really long, and that comes into play quite a bit with this family of model. So sometimes you choose the synchronous updating because computationally it is faster, right? Sometimes that is the reason that you make a certain choice. Okay, so this particular paper had a generalization of the DW model. Sorry for going back, I just wanted to make sure that. At each discrete time step, uniformly randomly select a pair of agents in network. If they're close enough, they compromise in an amount that's proportional to the difference. Is a choice that we made, and otherwise they don't change. And then you can ask various questions and look for phase transitions. Here are some equations. So here's my ith node. I'm counting time discretely. And if we are within this confidence bound C, so C is an important parameter, you can think about heterogeneous generalizations of this as well. If I'm within this bound C, I will compromise by the amount of this difference. And otherwise, I will stay the same. And the other node who I'm interacting with will also change by this amount. And the I comma j versus j comma I is because it's changing the opposite direction. So that is correct as stated. And otherwise, it will not change. Right? So I and j are the only nodes that are potentially being updated in a given step, the way we've written this down. And then you see what happens. I'm going to point to this one on the right because I know this is a complicated slide. Again, choice of random graph model is useful. The vertical axis is a confidence bound C. So the higher C is, the more likely a compromise is going to occur. The horizontal axis is what we call the multiplier. There are different names for this in different papers. If you go between 0 and 0.5, it's traditional to actually stop there, but we went from 0 to 1. the higher C is, between closer to 0.5 C is, the more you compromise when the larger amount by which you compromise when you choose to compromise. If you go beyond 0.5, that's an over compromise. People don't usually see it. It just makes the thing at least mathematically symmetric if you you can see asymmetry from numerics. The color is a natural logarithm of the convergence time, and the most red thing means we gave up and we bailed out and had not yet converged yet by the time we did that, and the number that we used is okay. So GN comma 0.1. This is above the giant component phase transition for Erdős-Rényi. What happens there? You actually get this curve, and there's a paper by Susan Fennell and James Gleason and others where they have a heuristic derivation of this curve. That's why I like to show this particular one. We only did numerics, and so there's a heuristic explanation for a curve of a transition between the behavior above, where things are going relatively fast, and below, where they're either not converging or converging very slowly. You can ask how certain ways of generalizing this work. So with Heather Brooks, we added some median nodes. You can think of these as zealots if you wanted, but we were interpreting them as median nodes. We got the locations for a certain numerical experiment. We got the locations of the media from the media bias chart. The median nodes in this model are not allowed to change their opinions. We impose that. So we modeled that by them having only out edges, no in edges. And then we have a bounded confidence mechanism, but it's users interacting, or accounts rather, interacting with tweets. I made the change because users don't map to accounts one-to-one. You have accounts interacting with tweets, and if they actually share something, they change their opinion. So it's a bounded confidence mechanism of what just has been tweeted. Okay, I'm going to show this plot in the interest of time and the interest of making fun of certain media outlets. This thing on the left comes from the media bias chart, actually version 4.0 from Ad Fontes. There are later versions of it. We have normalized their values, go from -1 to 1, so most liberal to most conservative. One thing that they have, and we use this in the model with Heather Brooks, so that's one thing this paper has that's not usually in these models, is that we have not just a value of an opinion, but we also have a content quality from the worst of the worst to sophisticated. In this plot, there are some number of media outlets, 65 or something, I forgot the number, that were present in the data at the time. The size of the dots is proportional to the number of Twitter followers that their main Twitter account had on the particular day that we checked. The color of the dots does not mean anything. That is just for visualization. And the largest ones in terms of number of Twitter followers that day were CNN, New York Times, Reuters, The Economist, and Fox News. We start with an initial condition of a bunch of other nodes that are not media nodes, just uniformly at random. The color and the horizontal axis on this series of plots mean the same thing. The color is just for visuals. So we've started them uniformly at random in certain spots, and they're sharing stuff from certain quality, which we also chose uniformly at random. Time 1, and we're looking at the ideology of the content that they're sharing as we move through time. This is using a bounded confidence type of mechanism. Equals 2, 5, 15, 25. And by t equals 122, you've more or less got an echo chamber situation where you've got one big group that's in the center, round over here, maybe shifted slightly to the left of 0. And you've got one big group over here, which is farther to the right and lower quality, lower quality, around over here. Rapid fire. Okay. There are many different types of models, and my goal was to sort of, at a general standpoint, introduce you to some questions that people ask, but then to hopefully show a couple concrete examples of how those questions might manifest in specific papers, right? There's lots of work by lots of people, including many people in the room. And again, I'm showing mine because I know my work better than I know other people's work, and just for concreteness. I showed examples with threshold models, voter models, bounded confidence models, environmental models. There's lots of others. Interactions between social dynamics and disease dynamics. Those need to be in those types of models. And types of questions many people ask: how does network structure affect dynamics? Is there a consensus? Or how many opinion groups form? Are there a steady state? How long does it converge to a steady state if you even get to one in the first place? And a very tough question. I think it's tough. How can we tell when one of these models is good? And I'm using the word good. I'm not using the word correct because I think correct is basically impossible. But good can have different meanings, so useful or whatnot. Um, I mean, all models are wrong in other cases as well, but I think it's really much more extreme when it comes to social dynamics than when it comes to other types of things that we study. And I worry about that. Okay, so some recent papers and work in progress. So if you want to look at more specifics, there's one paper that we put bounded confidence models on hypergraphs, and we did this in such a way that it enhances convergence for a certain reason, but you could generalize the hypergraphs in a way that does not enhance convergence. We have an adaptive bounded confidence model. One thing that you have to worry about there is if you're going to have a discordant edge, you now have to define what it means to have a discordant edge, because you don't just have an edge that has a 0 node adjacent to a 1 node. So now you're forced to make a choice of what that means. And so in this paper, we make a particular choice and look at consequences. We have a paper on spreading cascades that's on the way. We have a paper with smooth transition functions on the way. This one, by the way, is the one why I was talking about having a probabilistic kind of thing in the limit and a smooth, still probabilistic, but have a smooth, a dynamical systems type of calculation of when you're not in the limit and worrying about that. So there's a paper in which we're actually worrying about it. We have one with heterogeneous node activity levels. This will be out very soon because my student Grace is going to be starting an internship, and it will be better for all of us to have this online before the internship starts. So you should expect this one hopefully this month. Another paper by Kai-Yan Peng, which is bifurcations in a multiplex majority vote model. I don't know if that's going to be the title. She's starting a job at Facebook, aka the belly of the beast. So we definitely want this online before the job starts. And so we have agreed that we're going to put this on archive and submit it by July 7th. If you want to see this now, her thesis is online. This is chapter 4. All right. So with that, I will conclude, and we can have questions and coffee and stuff.
Thanks a lot for a beautiful overview talk. As we said, we have like an extensive discussion session, and I've seen already many questions on the web, but maybe one or two short questions. We take Yes and Pavel.
Hey, thanks for the great talk. So I'm very sympathetic to the, you want to work on something where you can actually impact the real world, and then you're using these models, and if they're going to be tractable, they can't be correct. But do you have like an example, just illustrative, of where you thought there was like a concrete proposal, either like at the policy level or the individual level, that kind of came out of these models, where you say, well, the model wasn't correct, but we still captured some general phenomena that we then thought there was something kind of real world you could draw from that?
So I'm not familiar with policy stuff from the social models. There's certainly policy stuff from the disease models, because a lot of people from, say, the network epidemiology community and others in the networks community were advising various governing bodies. And I think that there are some notions of behavior that got put into those, but I don't think they were actually like coupled models. They certainly had notions of, say, realistic style random graphs, say in the form of generalizations of configuration models that had appropriate mixing. So there was notions of abstraction, but I don't know how much behavior they put into those. I think there's some, but that's the only example I can really think of. Like, I can't think of like a raw opinion model that itself was informing policy. And I don't want to say it hasn't occurred. I just don't know an example offhand.
Thank you for the talk. I am from quantum field. So first question, just quickly, you used this concept of majority illusion. How you define it, how you detect it? First thing. And the second, all these models are classical in the quantum sense, or in this field, are there any trials to use this quantum contextuality to describe some of the behaviors? Thank you.
So the majority illusion, so the idea is that you survey your local neighborhood and you just say, okay, if I only look at who's on my friend list and what they're posting on Facebook, maybe the majority are going to be voting for, I don't know, for Hillary Clinton or something, but that's not the person who won. So the way that you would detect it is that you would count things in an ego network, and you would compare that to the count in the whole network. I mean, that's an observation, but that's the way you would do it. I didn't understand your second question. Do you want to repeat it?
All right, so maybe we will just pass it to the
Okay, that's fine.
because quantum contextuality is something that
I'm
requires
sorry,
a lot of
what word?
quantum contextuality.
Okay, I don't know what that is. I'm
No,
sorry.
that's okay. Just we'll discuss later. Thank you.
It's nice. Keep it for the longer discussion. I propose we take a coffee break, but and if you have questions, either put them on Slido or remember them. But let's thank Mason again for a great talk. And we come back 10:30 for the rest of the morning session. Coffee and pastries are in the canteen. You can follow me or others. Thanks a lot. It was beautiful.
Thank you very much. Oh, good. That's perfectly.